Great to meet you. I'm talking about some interesting topic, model-free optimization approach, and we applied this to dynamic renewable resource management problem. So basically, we are going to solve bi-level optimization problem. In the sub-level, the normal optimal control problem will be solved in the viewpoint of fishing farm. So they would like to maximize their profit. And in the upper level optimization, we would like to set some control by government. So we'd like to set the maximum harvest rate in the fishing company to maintain a certain stock level at the end of certain time. So basically, the contents is first introduction briefly what's the problem and what's the traditional approach, optimal control approach for single company, the fishing company, for example. And we would like to apply the model-free approach for the upper level, the optimization problem. And I would like to give some example of fishing company with renewable resource management and briefly conclude this presentation. So first, let's consider example of fishery problem. So basically, the stock level, the population of the fish depends on the harvest and also reproduction. So it's a basically dynamic problem. And also there is uncertainty. The fishing company would like to maximize their profit. And so if we go over the control range of the viability, we'll end up with deflating all the fish stocks. And also there is a competition. If we have multiple companies in the fishing industry, there will be competition and also gain. But we didn't go deep in the competition in this presentation, but we would like to give some sample interesting example for me. The sustainability viewpoint, we can connect this to the sustainability is connecting the bridge, connecting the present and future. So it's going to solve the dynamic issues. And also, this will be a systematic preparedness for the future, especially for extreme events. So we would like to, life is full of uncertainty, so we would like to manage it with some model if we can. And that's our goal is to maintain the level of the stock for sustainability issues and balancing environment, economic, and societal needs for sustainable development will be also important because the resource is limited and there will be competition. If we do not have any control, we'll finally end up with depleting all the renewable resources. So it's more complex and complicated than what we might imagine. The traditional approach is solving the company optimal control problem. They would like to maximize its profit. So its objective function J will be maximizing J, and inside the integration of infinite time, for example, we have discount rate, and out of the revenue, subtract the cost, it will be the profit. And it's the very similar problem, the example problem with fishery. And the subject, this optimal control problem is the subject to dynamic constraint. dx of t over dt is a function of resource growth rate. It's a reproduction rate, growth rate of itself, and ht is a harvest rate. So in the single form, they would like to maximize the harvest, and they harvest more, they sell more in the market, and they would like to maximize the profit. But in this case, the single form do not consider the sustainability issues. So if they can catch every fish by the end of their control plan, they will maximize the profit and they don't care. So we would like to set some constraint on the E of t. E of t is the effort of harvest, and we would like to set some constraint, E of max. That will be the upper limit of harvest. And this will be usually done by government and other upper level organizations. And the growth rate will have similar form like this. So we would like to introduce the maximum sustainable yield. At that point, x sub msy, the yield rate will be maximum. And if we have fewer fishes, the reproduction rate will decrease. And if we have overcrowded fish, it will also decrease the renewable resource refresh rate, growth rate. So in case if our optimal stock level is x star, then if the initial condition is greater than x star, we would like to maximize the harvest h of max. After then, the stock level reaches optimal level. We would like to keep the same harvest rate with growth rates. They would like to extend our sustainable resource management. And then after control time of 2, the company would like to catch all the fishes. They would like to maximize their profit. and it will end up with at time t, maybe t will be, large t will be infinite, and there will be no fish at all. And in case the initial stock x naught is smaller than x star, we'll wait, the red line shows we'll wait until the stock level reaches the optimal. And then they'll keep the constant rate with the maximum harvest rate, and they'll end up with catching all the fishes together. So in the viewpoint of stock level, the fish stock level, if the x star is greater than optimal, it will decrease and keep the optimal value x star, then it will be depleted at the end of time. So this is the problem of single firm maximizing their profit. And we would like to put some constraint and control over this by controlling the max harvest rate to make sure we have certain level of stock. So traditional model, we know that the simple mathematical model is very simple, approximated one, but still there is a lot of factors we didn't consider in this mathematical form. So we cannot solve exactly very well this problem. And also, more than that, the actual population can never be measured exactly. There is no exact measure to count the number of fishes in the research. Even though we solve this very simple problem, simple formulation, we would like to control this E of max. We need carefully control the stock level, but this will make this problem bi-level optimization. This is sub-level companies max profit optimization problem, and the upper level we would like to control E of max as a new control variable. This will be from the government point of view, and we would like to keep the same stock level xt as a state, and this E of max will be new control in the upper level. So new perspective is a bi-level optimization problem. It's very difficult to incorporate or embed this first optimal control problem into another optimal control problem because it's not simple ordinary differential equation. So we considered a model-free dynamic optimization approach that will be explained later, right after this. So unconstrained optimal control problem, this is the normal form of optimal control problem. But the dynamic constraint equation 2, x dot of t, we assume we have no idea of this dynamics. Actually, this will be the result from the sub-problem, but we cannot simply formulate in this closed form way. So without this, we collect data. Instead, we are going to collect data, and out of input and corresponding output data, we would like to iteratively find what's the optimal control trajectory that makes this problem optimal. So we got the idea from the alternative necessary condition. This is another form of necessary condition for optimal control problem. And the Hamiltonian, the derivative of the Hamiltonian, total derivative with respect to Lagrangian, the integration, the objective function integrand, and also adjoint lambda and Hamiltonian h. Then if this equation satisfies the necessary condition of first order condition, the result becomes 0. That means if the control trajectory is optimal, the result is the Hamiltonian should keep the constant value throughout the time, control time. So we got the idea that the constant Hamiltonian can be used as an indicator of optimality, even though it's a sort of necessary condition. So we developed the algorithm to collect the data and set the objective function L, the objective integrand L, analytically, maximizing the profit or minimizing cost or reduce the minimum time of the control. After that, we observe the control U and state X data. It's a time series sequence data. We don't have any structural dynamics model, and only use the sequence data and compute the X dot is a function of F, and it's derivative with respect to X, and also Lagrangian with respect partial derivative of Lagrangian with respect to X, and estimate adjoint and Hamiltonian and check the Hamiltonian is constant or not. If the Hamiltonian is constant, it's already met the necessary condition, so we may not be able to find a better solution. But if the Hamiltonian is not constant, we would like to change control trajectory U. It's a sequence of U of t, and also we will measure the corresponding state x of t. And out of this iterative loop will working again and again until we get the constant Hamiltonian. So the idea is also when we are looking for the better control trajectory, we are not just trial error and seek which just this way and that way and find a better one. We can find the better direction mathematically using the Legendre transformation in the calculus of variations. And that is, if we would like to keep constant Hamiltonian in the tangent line over the Lagrangian surface and trajectory. If we would like to keep constant Hamiltonian, that gives information in the y-intersect of tangential lines. There will be some value. What should be the y? Okay, let's go that. Yeah, time's up.
Yeah, can you?
1 minute.
Yeah.
So we can increase and decrease control value over time with this information. And the example shows the fishery farm with the upper level is annual control of government. We would like to set harvest level annually. And the lower level, the company, the fishing company would like to maximize their profit with a multi-year period. But every year, the government will set new constraint maximum level of harvest, and the company will renew its control policy. And this result is the green line is the increasing little bit the allowance level of harvest, and the total stock is decreasing. Even though inside the company this is more complicated, but it's the outside view of the upper level. And after applying the model-free optimal control, we was able to find the objective function is minimizing the harvest time, harvest limit variance. So we would like to minimize our interference to the free market. So the result is the red line is the initial trajectory, and we studied it from the red line trajectory and locally find the improving curve. So the result is the constant U is meaning the government will not change any value of the maximum harvest, but we would like to know what's the should be good initial value, and the X is the upper graph is the stock level, and it reaches the 300 fish after 10 years. So that was our terminal constraint. So the conclusion is we proposed a model-free optimization approach for complex dynamic problems, especially for bi-level optimization problem, and showed this framework is working for some renewable resource management problems. But still there is some limitation in the approach. It is not free for all. So we assume it will work with consistent governing law in the upper level and works for monotonic control state patterns. So if there is inflection point or concave or convex curve, this model-free approach may not converge to the final solution. So we are still working with the sensitivity analysis of this renewable market problem and also robust optimization, but this is what we prepared for today's presentation. Thank you.
Thank you very much.